Um, so when I was looking at the schedule of what I'm supposed to cover today, um, so really we're still in that first week of August 28th. And on one hand, it turns out that I've pretty much covered that stuff already last Wednesday, except I also found out that from what's coming up, like when we get to chapter 2 in the notes, I allowed myself one week to get through all of chapter 2, which is kind of insane. So I think it'd probably be best if I went ahead and let myself get a little ahead of what the schedule says so that I won't fall behind later. But definitely means can be mellow about it. So, and it probably will be the most laid back 700 level class ever. Okay. Now, okay, so I did all that last time. Okay. I want to give some examples of partial differential equations. A few came up last time, but there's so many. Okay. Now, basically any introductory class on PDEs, they're pretty much three equations that should always be discussed. Whether it's doesn't matter whether it's about numerical methods or not. We have Laplace's equation, and that is the equation where the Laplacian of u, which, to refresh your memory from last time, it is also written as like gradient squared u, which is uxx plus uyy in 2 dimensions. If it was 3 dimensions, I'd have like plus uzz. So however many variables you have, that's how many terms you have, is equal to 0. And then there would be some kind of boundary conditions to go with it. And a related equation is Poisson's equation. And all that is Laplacian u is equal to some function. So that's given. Okay. Laplace equation, Poisson equation, one particular application is modeling electrostatic potential. So, for instance, if a right-hand side function describes some electric charge, then a solution U represents the potential associated with that charge. Okay. So that's me pretending to care about applications. Really, I'm just here for math. Mm-hmm. So, okay. Like when I would give a calculus test, and the problem would be like evaluate this integral, and like I say, compute the volume of the area of this. But really, it's about an integral. So some students would be snarky. They work out the integral, come up with a number, and then they'd write next to it units cubed or something like that. They're like, why? You're just being a jerk. So. Okay. All right. And actually, all three of these fundamental equations involve a Laplacian. The heat equation, derivative with respect to time, is equal to the Laplacian of u. And there may be a coefficient in there, but you can always do some change of variable to get the coefficient out and just have u dt is equal to Laplacian, where u refers to temperature throughout whatever spatial domain you have. There may be additional terms, like if there's additional, like if I have some external heat source that would affect the temperature, but I would add that term onto the right side. Okay. And then there's the wave equation, second derivative with respect to time, is equal to the Laplacian. And u, in this case, refers to displacement. So, for example, if I'm in one dimension, I would have like a vibrating string. So u would describe the displacement of a string as it is vibrating. So displacement from its equilibrium position. Okay. So a lot of PDEs from applications are built off of these, like more general forms of these, and they involve various coefficients and extra terms, etc. So certainly a lot of discussion of numerical methods would be based on trying to solve these equations and then adapting your methods to solve other ones. Okay. All right. Now, okay, so other examples of PDEs. We have, this one's closely related to a wave equation. An advection equation ut plus ux is equal to 0. Although really I don't have to have a plus in there. I get a plus or minus. And whether it's a plus or minus indicates a direction of propagation. So when I say advection, this is meant to describe, for example, like propagating waves. So actual or movement of a substance, suppose you have some substance embedded in a fluid, it's moving through a fluid. For example, some sort of dye dropped into a solution, and how's it propagating through a solution? So if something is moving with an actual finite speed, as opposed to seemingly instantaneous, that's advection. Now I can write down a solution of this. It would be something in this form. Some function of x sorry, that was totally wrong. So I need to cheat and do a little calculus in my head here. So du dt is f prime, or minus f prime. And u dx is equal to f prime. So yes, that's right. So whatever sign you have here, you have the opposite sign here. So plus minus, minus plus. Now, where f, a function f, has to be something that's given as the initial condition. So for any time-dependent problem, like this one, you're going to have one or more initial conditions. So given initial condition, if you don't have any boundary conditions to think of, and I didn't bother including any here, we can describe what the solution looks like at any time t. Now, let's bring some lower level math, like some of you are teaching 101. So if you haven't been teaching your students this already, you will, I'm pretty sure. So if I have, say if I choose the plus sign here, and I have the graph of f of x, what is the graph of f of x minus t? How does that relate to just a graph of plain old f? Yes, shifted.
To the right.
Yes. Yeah. Thank you for making it clear, Sarah, with a head bob. Yeah.
Oh, yeah. To the right.
Yeah. Yeah, and then if it's plus, then it's to the left. So what we have here is if I have a plus sign, the solution is some sort of wave described by f at the initial time that's propagating to the right. That's what the solution would look like if you were to plot it. And then if I have a minus sign, then it's propagating to the left. All right. So this is how solutions of advective problems behave. That just that kind of propagation going on, but you can observe over time. Now I should mention the wave equation I wrote over there. If I go back to one dimension, so it'll just be utt minus uxx equals 0. But if you think of this as differentiation in respect to t squared minus differentiation in respect to x squared. In other words, it's applied twice. So here I have what's called a differential operator applied to u. And computing higher order derivatives are powers of differentiation operators. Now, let's bring a little more low-level math into this, except in a high-level context. Now, how do you think you can factor that differential operator? Yes, you can treat it just like a difference of squares. Only because these operations commute with one another. Like, if I differentiate something with respect to x first and then t, or t then x, you get the same result. So because they commute with each other, you can factor them. So dt minus dx, dt plus dx. So in other words, this wave equation, you can think of as breaking down into a product of two advection equations, one each with a plus or minus sign. So that means if I have a wave going left or right, satisfies the wave equation. And in fact, the solution of a wave equation, well, those of you who've taken a PDE class, you've seen, I'm going to pronounce it wrong, a D'Alembert solution. That is expressed as a sum of a left moving and right moving wave. So that's exactly what's happening here. So this equation, that's first order. You have waves propagating in one direction. Second order wave equation. your solution is propagating in both directions. You have your initial data, it's going to split off and move to the left and right. Okay. Spent way too much time talking about that one. But, okay, well, actually, these I already did. Okay. So, questions about the weird stuff that happened there? This uses of one-on-one level math that no one-on-one student would ever care about. Well, they wouldn't know about it either. So, okay. Now, I've indicated advection. Now we can throw in other terms or other physical phenomena. An advection diffusion equation. So this has a similar form, ut plus some coefficient times ux, but then I throw in another term, the uxx. Is this recording? Hello? Yes, it is. Okay. It's happened sometimes where I think I'm recording and like, nope, the whole class is gone. Okay, so this is an advection term, but as that's indicated by the first derivative with respect to x. This is a diffusion term. Now, if I toss the advection term out, C is 0, I basically have the heat equation all over again. What does heat energy do? It diffuses. Like if you don't have any heat sources, without any outside interference, the temperature in a room is going to diffuse to a constant temperature over time, based on Newton's law of cooling. So that's diffusion. But this equation has both effects happening. Okay. I could throw in another term. Okay. So you need a coefficient. Okay. So if I have another term with just u by itself, no derivatives, that would be a reaction term. So modeling chemical reactions. So now we know how to express advection, diffusion, and reaction terms in a PDE based on the order of spatial derivative or not. Okay. My next example on the list I already covered. Here's one that's rather odd. It's popularly known as a KDV equation, but this is short for names. Looks very Dutch. Korteweg-de Vries equation. I'm sure I butchered that. So people everybody just calls it KDV. So it's actually a quasi-linear equation. So ut plus ux. This part I actually wrote down on the board last time as Berger's equation, but we have an additional term that makes it into something else. Epsilon uxxx. Okay. Now, this equation, which I haven't really dealt with in my research, although I'd like to, is rather unusual because usually when you have a nonlinear equation like this one, it's not possible to write down an exact solution. You just don't have it. Whereas with linear equations, all the examples I've done up to this point have been linear today. You can write down a solution formula, but not this. But not with nonlinear. But this is an exception to that. And the solutions, and it depends on other things like boundary conditions and so forth, they're called solitons. And solitons have a very strange property that if I were to draw a very crude graph, like here we have one soliton, then elsewhere we have another one, and over time, this soliton could be propagating towards this one, and what it has the effect of doing is it can pass through this, come out the other side, and not change shape. Like it just propagated to this larger one and was not affected, which is really unusual for graphs of solutions of PDEs to behave that way. You'd think there would be some sort of mixing or loss of substance or some sort of absorption, something, but no, it just passes through it as if it's a ghost. Strange characteristics that solutions of the KdV equation have. Okay. And then I'll throw in one more that is of particular importance, and also a real pain to try to solve. Okay. Navier-Stokes equations. There are different forms. There's compressible and incompressible. I'll write down the incompressible version. So it's a system of equations, ut plus, well, u is a vector quantity, so it's a function that has three components to it. So that's so really there's a system of three PDEs, and there's an additional equation that goes with it. Okay. Now, so Navier-Stokes is for modeling fluid flow, basically, and U represents the velocity vector of a fluid. So like X, Y, Z components. P is pressure. Okay. Now,
Is that after pressure, is that a U or a P?
this?
Uh-huh.
Oh, it's a Greek letter nu.
Oh, okay.
Yes. That's why I drew it rather funny.
Wait, what is that?
This?
Yeah.
It's a Greek letter nu. But yeah, most people just write V.
Oh, it's like that. What does it reference? Straight.
Yes, yes, yeah.
What does it reference?
Within this equation,
Yeah.
it is some coefficient.
Oh, okay.
Yeah. Right now, I can't remember. Okay. Yeah. So I want to talk about this additional equation, which is saying that the divergence of u is equal to 0. Now, divergence is something that's covered in multivariable calculus. Now, u, because it's a vector function of x, y, and z, it's called a vector field. So it's representing the velocity of the fluid throughout your domain, in this case. Now, the divergence of a vector field indicates the tendency of a vector field to actually literally diverge from its current location. So when a divergence is 0, that means there's no tendency to spread out. So that's why it's incompressible. That's what makes it incompressible, that the divergence is 0. But the fluid tends not to change volume. So, now what is a divergence? That's, if I write U having 3 components, let's see, U1, U2, U3, that represent X, Y, and Z components. So divergence is equal to partial of U1 with respect to X plus partial of U2 with respect to Y plus partial of U3 with respect to Z. Okay. Use the 1 as a subscript. And I'm saying that's 0. Now, this equation can be used to eliminate one of these from the PDE. So in other words, this is called a differential algebraic equation, or DAE. Because you have this extra equation that says that it's incompressible. That's further constraining one of the derivatives of your solution. Now, those of you who know my recently graduated PhD student, Brianna Bingham, her dissertation was on the compressible Navier-Stokes equations that did not have this. So it was just a plain old PDE. Still a real pain in the butt to solve. So in that case, volume change does happen. So there's a prize for like $1 million for solving Navier-Stokes equation that's still unclaimed. So, but not solving numerically, like coming up with an exact solution or something like that. I don't think anybody will ever do that. People are solving it numerically, including Brianna. Okay, so it's one of the best-known PDEs out there. Real pain in the butt to solve. Because
that's not one of our homework problems, is it?
No, we are not touching that. Because this right here makes it nonlinear. I think all of your problems involve linear PDEs. So yeah, that's okay. You'll suffer enough.
I'm sure.
Okay. All right. So those are several examples of PDEs. Of course, there are many more that I could go through, but okay. Oh, we're about halfway done. Okay. Now, so next I'm going to talk about central concept, not just for PDEs, but applies to other kinds of problems too, and that is well-posedness. Basically, talking about the solvability of any of these problems. So what does well-posedness mean? So PDE is said to be well-posed if it satisfies 3 conditions. First, a solution has to exist. Which is definitely not short. I will show you an example of a PDE that looks like any other, but it turns out it cannot be solved. Second condition is the solution must be unique. So you could have well-posedness break down if, for example, there's no solution at all, or if you have infinitely many solutions. It's kind of like when you have systems of linear equations, like from your linear algebra class, and like it turned out to be inconsistent, so there was no solution, or or if you change the right-hand side, it may have infinitely many solutions. It's kind of like that. So I'm talking about for PDEs, but really could apply to other things too. And then there's a third condition that's a little harder to digest. The solution depends continuously on the problem data. Now, what do I mean by the data in this case? Data can mean, when we're talking about a PDE, data can mean many things. It could mean either initial conditions, so like whatever function is specified as the initial condition or boundary condition, or if a PDE has coefficients, well, they all do, sometimes it might be equal to 1. So that also counts as problem data. Now, what does it mean when I say solution depends continuously on the data? A way I prefer to describe it, rather than this typical phrasing, is a small change in the data does not lead to a large change in the solution. So if the problem data, like a coefficient or initial data, was tweaked just a little bit, that should not throw off a solution to a large degree. Now, small change, large change is not quantified here. It's like one of those things you know it when you see it. Okay. In numerical analysis in general, so beyond PDEs, another way of describing this is we're saying that the problem is well-conditioned. And therefore it's ill-posed or ill-conditioned if it doesn't meet these conditions. Because an ill-conditioned problem is one where, like for instance, you're solving a system of equations, Ax equals B. So this came up in 610 last semester, where you change A or B a little bit when solving Ax equals B, and the solution is X is thrown off by a lot. So an ill-conditioned problem is similar in spirit to an ill-posed problem for a PDE. These conditions have a name. They're called Hadamard's conditions. So we definitely want to know if PDE problem is well posed before we even try to solve it, because otherwise, good luck. So. Okay. No. Okay. Now, I'm going to show you an example where I have one PDE, but different conditions on a PDE, like boundary conditions, that could cause any of these or actually any of the first two conditions to break down. So whatever type of problem data you have can play a significant role in determining if a problem is well posed. So if you have a PDE, you can't just say, oh, this PDE is well posed. It depends on what data you pair with it. All right, so PDE is uxx plus u is equal to 0. All right. So I'm going to write it a little differently. U double prime is equal to minus u. So let's again step to lower level math, but not quite as low level as I did before. Can anyone give me, we should be able to, or somebody, an example of a function where taking the function's second derivative negates the function. No? Like the second derivative of the parabola quadratic would be a constant.
Right. Okay, that's what you're
Yeah, yeah. Because really, yeah, so the second derivative keeps the function the same, except for sign change.
It's just negative.
Yes.
Because sine.
Yes. There you go. Yeah, sine over cosine. So in fact, I can say u of x is equal to some constant times cosine plus another constant times sine. So for any choice of a and b, this is a solution. So we can call this a general solution. So now it's not unique, certainly, because we can pick any a and b. But we would not have a PDE by itself. We would have some sort of conditions on it. Like I haven't specified the domain of a problem yet, so I wouldn't need to do that. So if we have an actual problem to solve, like a boundary value problem, then we can determine if a solution exists and is unique. Okay. So what I'm going to do is I'm going to specify a few different problems where I nail down the spatial domain and boundary conditions. So because we have a second derivative as a second order equation, in order to nail down a unique solution, I need two conditions to impose on. Whereas if it was a first order equation, I'd only need one condition. So I can specify the value of a solution at 2 points. We can think of those as boundary conditions, and then see if we have a unique solution. So for example, let's suppose I specify that u of 0 is 0, and u of pi over 2 is equal to 1. So can anyone tell me, well, if there's a solution in it, and also what it would be? Recall your trig, which may be a dicey proposition for some and others.
So A, like make you plug in 0 for x.
Oh, okay, let's go ahead and approach it. Well, if you do plug in 0 for x,
So that just issues of A, and it's sine of 0, 0. So it's just A.
well, yeah, u of 0 is a, but because it has to satisfy this, what does that tell you?
That A is 0?
Yes, it does. A is 0. Because it has to be gone. All right. So then what? Yeah. So the first condition tells you that there's not going to be a cosine. Now you're left with b sine x, but you got to figure out what b is.
Would you do it the same way, plugging in pi over 2?
Yes. What happens?
I don't remember my trig.
Okay, who can tell me what sine pi over 2 is?
Is one the same as
Yes.
pi?
One.
It's 1.
Okay.
Yeah. So therefore, b is yes. Yeah. So we have. That was painful. Yeah, sine x, and that was the only one that worked. So we have a unique solution. So okay. Well, that's so much fun. Let's do it again with different conditions. All right. So again, I will go with.
So
What?
Since it's a unique solution, can we say that it's well posed or no?
Well, we've not looked into the third condition, continuous dependence on data.
Okay.
It has been shown that this problem is well posed, but we're not really gonna. Yeah, we'll just
Okay,
gloss
that's
over.
not
We're gonna gloss over that. But like, yeah, if I decide to have a coefficient in front of u, for instance.
Mhm.
Well, actually, let's go ahead and do that. So if I have uxx, so really it's u double prime is equal to minus c times u. So it's negating, but also multiplying by some constant c. And I'm going to assume for convenience that c is positive, because c is 1 in this case, and we care about values near 1. Because if c was negative, that would change things a little too much. So what kind of function where you take a second derivative, it not only negates it, but it multiplies it by a constant? And if c is 1, you're going to get cosine sine. But if it was some other value, so we're looking at something of a similar form. Well, there's squaring involved, but not that way. Okay. Good job.
Ask the question again.
All right. So we know that if we take the second derivative of sine or cosine, it negates it. But now we have the additional effect of multiplying it by a constant. So what, if you think of your differentiation rules, what differentiation rule causes derivatives to be multiplied by something?
Exponential.
What?
Yeah, it has an exponent.
That's all it really is.
I'm not thinking of a type of function. I'm thinking of a differentiation rule. And there aren't many of them, so power rule, quotient rule, chain rule.
Power rule.
I feel like you're helping us so much, so we're making it hard.
Yeah.
Okay. I'm just debating how long before I put you out of your misery.
Is it the power rule?
No.
Okay, good. Chain rule?
Yes, it is a chain rule.
Well, I feel like changing the power rule goes in and
Well, they kind of do, because it leads to a general power rule, but that doesn't help us here. But if you think about chain rule, like if I have, okay, what's the derivative of sine 2x?
2.
Yes.
Yeah.
Okay.
Oh, yeah. Okay, so pull that coefficient out.
Yeah.
Oh, yep.
All right. So second derivative of sine 2x.
Negative 4 sine x. Sorry, or 2x.
Is
Oh,
it
4. I mean, what was the second?
negative 4.
Say, what was the second derivative?
Second derivative of sine 2x. You differentiate it once and you get 2 cosine 2x. You differentiate it again and you get minus 4.
Minus 4 cosine 2.
Not
4.
cosine.
Sine.
So it's back to sine. Yeah. So whatever coefficient you had, the 2 squared is what comes out front. So the solution, the general solution is a cosine square root of c x plus b sine square root of c x. Because, so then if I take second derivative of that, I flip to cosine, then back to sine, I get square root of c once, then get it again to become c, and then a minus. Okay. So, did anyone see that? Okay. Or you can try yourself to confirm it. So, here c is 1. If I change c from 1 a little bit, it's not really going to change the graph of this all that much. I mean, yeah, you'll see a difference, but it's not going to like something morph into something different. Like a gremlin fed after midnight, it's going to change some monster. So this problem is well posed. I mean, at least intuitively you can see that that's definitely not a proof. But so it is. You're taking someone's word for it. Okay. But now we look at different boundary conditions. Things can go wrong. So, all right, so we'll keep u of 0, 0. But then I want u of pi, instead of pi over 2, to be equal to 1. So, u of 0 being 0, just this condition alone, we saw last time we end up with b sine x, because that caused the cosine term to drop out. So what happens when you try to make it also satisfy the other condition, u of pi equal 1? Yeah, why doesn't it work?
Sine of pi is 0.
Yeah.
And 0 times b is 0.
Yeah, so you're never going to make it equal to 1.
Yeah.
So it fails in the first condition. Solution does not even exist. So.
But, so for it to be, like, this example is not well posed.
Right.
So you can't say if a PDE is well posed or not unless you have boundary conditions.
Yeah, you need the whole problem.
Okay.
Yeah.
Because it can be well posed for some boundary conditions, but not for others.
Right, and actually, I was, I think I may have been negligent when I wrote this on the board. Because look at your notes. Did I say if PDE is well posed? If? Yeah, I goofed. So the actual definition says the problem consisting of a PDE and its initial and or boundary conditions. Yeah, so you have to throw those in for the definition to apply. So, whoops. End of day laziness. Okay. All right. So now, let's change this a little bit. Well, keeping u of 0, 0. So we have some knowledge of what the solutions would look like. And then u of pi is 0. So what happens with a solution in this case? So we want to have a value for b.
B can be anything.
Bingo. Yeah. So in what sense is it not well posed? What condition does it flunk?
It's not unique.
Yeah. So a solution exists, but is not unique. There are infinitely many solutions. So that is still ill-posed. Okay. All right. Okay, only 7 minutes, but I just have one more example, and then it's a natural stopping point. Well or ill-posedness. Okay, so I'm going to write down 2 problems. That are pretty similar to each other, but one is well-posed and the other is ill-posed. So the PDE itself is the heat equation. And then I'll throw in some boundary conditions, right, on the interval 0 to 1. So 0t. So if x equals 0 and x equals 1, solution is required to be 0, so fixed temperature. And then we have some initial condition that's necessary for uniqueness. So that's one thing essential about boundary and initial conditions. So this is boundary conditions and initial conditions. We definitely have to have those to have any chance of uniqueness. But as we've seen, once we have that, it's still not a guarantee. Okay. So now, if I have a problem that has the same boundary conditions, same initial conditions, but a slightly different PDE, ut is equal to minus uxx. So this is called the backward heat equation. That is ill-posed. And it's called the backward heat equation because if I made a change of variable in time, like I replaced t with minus t, then that would cause a minus to appear. So here we're looking at heat diffusion happening forward in time, and now we just, basically you're taking it, moving, you're running it backwards, and that's this equation. So you may know this temperature profile at the end time, and you want to unwind to what it was before. Now, with these conditions, there is a solution in both cases. The solution is unique in both cases. So the solution is not continuously dependent on the data. Now, fortunately, it is not at all obvious just from writing this down why that problem is ill-posed while the other one is well-posed. There's nothing in how it's written to suggest why that is. What I'm going to do is, okay, I have 4 minutes. I'm going to nail down a specified initial condition, and that will allow me to write down a solution in both cases. So I'm going to specify the initial condition be equal to sine pi x. Because that way, if I plug in x equals 0 and x equals 1, I'm going to get 0 at both boundaries as is required. So for the forward or regular heat equation, ut equals plus uxx, I can write down a solution. I don't have time now to explain how I got it. Maybe I can talk about that on Monday. Well, something you learn in a class like 517, or I guess it was covered in 606, I don't know. Well, it should have been. So it's e to the minus t, minus pi squared t sine pi x. So for example, if I take the second derivative with respect to x, the only thing that changes is I get a minus and I get a pi squared up front. Chain rule. If I take the derivative with respect to t, The only change is, again, multiplied by a minus pi squared. So it satisfies that. Whereas if I have ut equals minus uxx, then I just have this. It just changes the sign in the exponent. Okay. Now, so let's suppose I change this initial data, the sine pi x, I change it a little bit. Like maybe I multiply it by a constant, just so the general form of solution would not be affected. What happens to this factor here as t increases? So we start at t equals 0, t is moving forward in time, t is positive. How does this solution behave over time? What does that e to the minus pi squared t do? Yes. Yeah, it goes to 0. What about the other one, e to the pi squared t? How's that going to behave?
It also becomes smaller, but it's positive.
No.
But it's
No. So, like, just take e to the x, for instance, as x is positive. How does e to the x behave?
Exponentially
Exponential what?
positive.
No. Growth. Decay, growth. That's the difference. So this exponentially decays to 0. This exponentially grows to infinity. All because of the sign of the exponent. So negative exponent, exponential decay to 0. Positive exponent, exponential growth to infinity. So if I tweak this a little bit, at t equals 0, it doesn't really matter that much. But because this factor is growing, whatever change I make here is amplified over time. So the solution at a certain time t, far away, would be changed greatly from the solution they had before I make a change. Whereas any change in the data in this solution, it's going to have negligible impact because all the solutions are going to 0 anyway. Yeah. So that's an example of failure to have continuous dependence on the data. If your solution involves exponential growth, you're out of luck. And this is really bad for numerical computation because you're always going to have some sort of deviation. There's always some sort of error creeping into your solution. If that error is amplified over time, then you can't trust your solution. So we need problems to be well posed to have a chance of solving them numerically. So we just don't mess with that backwards heat equation ever. Okay, well, I've actually gone a little past time. Sorry for making you late for practice. Okay, so let's see. Well, let's keep going through chapter 1. Next week, we'll have a full week finally. So I actually have an hour and a half class period. Okay, and I'll have this up tomorrow. I'm sure you'd love to watch it.